Good morning, everybody. So my talk today is on understanding, assessing risk and financial predictions by using Monte Carlo simulations. And so before I get started into actually the jump part of it, I wanted to give you an understanding of why at Raytheon do we look at this. So quarterly, our programs have to do what's called an estimate at completion. The estimate at completion is just an estimation of the total cost required to fulfill contract requirements at the completion of the contract. BAC-EAC is just calculated by taking the cumulative to date actual costs and adding the forecasting costs of the remaining authorized work. Why is this important to us? The EAC, we do these quarterly, and so they give us an early identification of contract cost performance issues. They allow us to identify and assess contract risk and opportunities. That's the major part of what I'm going to be looking at here. And we get to document those risks and look at risk mitigation or opportunity realization plans. So just in simple terms, because I'm going to use this formula throughout, is the estimate at completion, EAC, is just the actuals cum to date plus the estimate to completion. So what I'm looking at really is the estimate to completion. Our accurate EAC relies on us being able to estimate this estimate to completion. Once we get our EAC, we actually compare that to a budget at completion. We have some budget at completion that we need to meet. So when we compare it to that, we can calculate a variance at completion, which is just our budget minus our estimate at completion. If that number is positive, then we have a possible underrun. We have an opportunity. So we're going to give back maybe some money or spend it somewhere else. If our variance at completion is negative, then we have a possible overrun or risk. And so we're going to go through an example. I can't bring real data like other people, so I made up some fictitious program here. Our program has 4 major subassemblies within it that have to be manufactured to get a completed product. My product is called a logo. It's made up of 4 subassemblies, JMP, and the dot over the J. For my estimate of completion for this example, we're going to really use a very simplified, unrealistic example where I'm just basing it on manufacturing hours. I'm not looking at the cost of the products that go in here, but just strictly the manufacturing hours to complete these 4 subassemblies. So to date, I'm going to go look at how do I calculate my EAC. To date, I have 50 logo units that I've completed for this example, and I have 30 more to complete by the end of the contract. So I have the actuals, my cum to date, for the 50 completed logo units, and that's about $394,000. I have raw data for those 4 subassemblies of the 50 completed units. My raw data, when I calculated it, I've got the hours, the average hours for each of the subassemblies, and they're shown here for the different JMP and the dot. And so therefore, I could go calculate an average hours to complete each logo unit. So if I just sum those 4 numbers up, I get 157.5 hours. I could base my estimate to completion on that 157.5 hours by just multiplying by a labor rate of $50 per hour and estimating how much it costs to complete the 30 units left. So I just multiply that out, and I get about $236,000 as my estimate to completion. So now I've got my actuals to date, I've got my estimates to completion for my 30 units I need to go complete, so I can calculate my estimate at completion by just summing those 2 numbers, and I get $630,000. Then I can compare that to my budget. So for this example, my budget at completion is $600,000. So I calculated my estimate at completion of $630,000. So I have a potential overrun of this program of $30,000. I get that one number, and a lot of times that's what we go off, and we make all our decisions based on just this average data, but I don't know how likely is that number. Is that number really 30,000, or could it be as high as 60,000, or could it be as low as 10,000? I have no idea on how much risk is built into that number. So I'm going to use a Monte Carlo simulation to determine what is the probability that I'm going to overrun or underrun, and determine that range of overrun and underrun. For those that aren't familiar with what a Monte Carlo simulation is, just a really simplified definition here is it's just a technique that takes into account uncertainty or variability in the inputs to make an estimate on the outputs. So instead of taking a single value for our inputs and just calculating one number, we're going to go look at a range of values. So we're going to, if you look, I've got my 4 inputs here, my 4 subassemblies, J, M, P, and dot. And I'm going to form a distribution for each one of those. So those distributions might look like this. And what the Monte Carlo simulation does is then it randomly draws from these input distributions based on the shape of them. So it's going to draw for this M, it's going to draw more in the middle than it will on these outskirts here. And it'll take random draws. So one random draw might be where these red X's are. And then it would just sum those for my example, because I'm just looking at hours, total hours. Each of these are individual hours, and I want the total hours. So it would just sum these red dots, and it would give me the red dot over here for the total hours. And it would just keep taking random draws till it builds a distribution for the total hours. So that's what I'm going to do with this example. So now I'm going to go into a demo. And here is, I started with these, I've got 50 units I've already completed for this program, so I've got 50 data points for each my J, M, P, and dot. So there's my data set with those 50 data points in it. So now what I need to do is look at the shape of these. I need to understand how much variability do I have in each of these subassemblies. So I could just go up here and do histograms, and I've already got a script written here to do histograms. And there's the histogram of my 4 different subassemblies, my J, M, P, and the dot. So notice, some of these, this one could be kind of normal. This one kind of looks skewed here a little bit, and this one too here. So I've got quantiles, automatically calculates, and I've got the summary statistics. Those are the averages that I use just to get a 1 overall average. So it just took the average of all those data points, and I use that value. But now I'm going to use the distributions to go look at doing the simulation. So I need to understand what kind of distributions do these follow. Well, JMP has built into it in the same distributions where you can go up here and tell it, oh, not there, sorry. For each of these, you can go tell it I want to do a continuous fit. And it can fit a whole bunch of different distributions. I'm going to just tell it, fit them all. And if I scroll up here for each of the distributions here, now you see it's drawn a curve fit. It'll do multiple different curve fits. I'll show you here. Let me get rid of the quantiles and summary statistics. It's got built into it multiple different distributions that it looks at. So it fits, the one that's drawn is the one that it says is the best fit. There's these AICC numbers up here, and the smaller the number, the better the fit. Just because it draws a number on there doesn't mean it actually fits that data. And what it also has in here, so down here, the fit at log normal, if you go down to it and do the red arrow, you can do a goodness of fit test. And so then it'll do a hypothesis test that says, does this log normal distribution that I've chosen here fit this? And if these numbers are greater than 0.05, because we're testing the data is from a log normal distribution as there are no hypothesis, then that will be an appropriate fit. So we've got these different distributions for each of these. So this one that says fits a log normal. The M, it says it fits a normal distribution. If we come down here, it passes the test for normality. The P says a Johnson SI, and the dot, it says a normal. I'm going to look at the P though here. It says it fits a Johnson SI. I don't know what a Johnson SI curve is. I went and looked it up, but I'm still like, but I understand what a log normal curve is. So I'm like, well, it's the next in line. It's the AICC number's not too far off. I wonder if it fits. So I can actually go click here. Now I've got a log normal curve on here. Also, it's the green one. And if I come down here, the goodness of fit test for the log normal is right here. Its p-value is greater than 0.05, so it fits a log normal. So I'm going to use a simpler distribution. I'm going to use the log normal rather than the Johnson SI. So the whole purpose of fitting this, I've got my historical data, the whole purpose of fitting this is to find out what does this distributions look like. Because what I want to do is random draws from those distributions. I've got historical data, but I want to know what's going to happen in the future. What could these look like? So that's what the distribution gives me. So now to do the Monte Carlo simulation, what I've got to go do is I've got to go set up columns that have those distributions in it. So because I want to go do random draws from those distributions. So I went in, I've just got a data set here that just is blank, but I've set up, named my columns JMP and dot, and I've got a total hours here. And if I right click on this, I'm going to show you that I've actually added a formula to those columns. JMP has a whole bunch of formulas in here, and if you go under random, here it will pull from random, from all these different distributions, random numbers. So for my J, if you remember, it was a log normal distribution. I got the parameters from the fits before, so I didn't have to type them up here. But so it's a random log normal distribution with a mean of 4.6 and a standard deviation of 0.44. So I put that in to column J. Column M has a formula, was a normal distribution, etc. And then my total hours column over here has a formula in it that just sums my J, M, P, and the dot. So now that I've got those formulas in there, I can go add rows here. So I want to go randomly take a sample, and I'm just going to go tell it to take 10,000, add 10,000 rows. Boom, now I've got my data here. I've got information on what my total hours are going to look like. So now that's my output for my Monte Carlo simulation. So that's what I really want to go look at. So if I go draw a histogram of that, now here is my total hours histogram, and that's what I want to base my decisions on. I can go look at the quantiles, and I like to have these in by 10%, so I can go change that quantiles. So now I'm 80% of the time, my total hours is going to be less than 195.61. On average, or the median, 50% of the time it's about 147.9. So this is giving the programs now a little bit more information on where are my total hours going to be. I can get more information and more risk there, and I've got a distribution. I took this a step further. This is usually where I've ended with the programs right now, but for this, I've actually took this a step further because I want to know I've got 30 units I've got to go finish. So I really am going to draw from this distribution 30 times. To get my estimate to completion, I want 30 units out of here that fit this distribution and go calculate what's the total hours for those 30 units, because I'm going to need the total hours, sum those 30 units up to get my estimate to completion. So that's just what I was saying. The remaining 30 units should follow a similar distribution to the total hours. So to estimate the estimate to completion for the 30 units, I'm going to run another Monte Carlo simulation that takes random draws of size 30 from the total hours distribution. Then to get my estimate to completion, I'm just going to sum those 30 units up and multiply by $50 per hour. Now, if you remember, the formula for EAC that we're looking at is the actual scheme to date plus the estimate to completion. And I have a budget that I want to meet. So I can actually go put a spec limit in here when I get this distribution. And my spec limit is based on my budget. I'm going to assume my estimate at completion is right at my budget of $600K. I've got my actual scheme to date of $394,000. So I've got an estimate to completion that I want to meet of $206,000 or $206,000. So I'm going to use that as a spec limit when I go in and do my Monte Carlo simulation. So to do this, I've got my total hours and I've got a distribution on that just from the data that I collected just a minute ago. What I've got here, it might not be exactly with the fit that was on the previous one. This is from when I did it in a different time. But I've got the random, it fit a random Johnson SI distribution. So I've got that in there as the formula. So now I want to go collect samples of 30. So what I'm going to do is add in some columns here. And it's got an add multiple columns. And I'm going to just take some random samples of size 30. So I'm going to maybe just take 100 samples of size 30. So I'm going to add 100 columns. And I'm going to do this as a group of columns because life is much easier when you do that for this. And now I've got 100 columns out here that I've added. And I want them all to have this same formula in it. So I'm going to take these, and I'm going to copy the column properties from this one. And then I'm going to highlight my 100 columns, and I'm going to paste my column properties. So now each one of these, if you look at it, has that same formula in it. From here, I want size 30 samples of this. So I'm just going to add 30 rows. And when I do that, now I've got 100 samples of size 30 of my total hours. For my estimate to completion, I need to sum those. So I can go up here to Analyze and do a Tabulate. I like the dialog box instead of the interactive there. So I want my 100 samples, and I want to take the sum of them, and it creates the sum. So now I've got a sample of size of 100. That's the total sum hours. I'm going to put this in a data table because I want to do stuff with this. And where'd my table go? Where'd it go? Let's try that again. I don't know where it went. Oh, that's show tape. Hey, that's it. I hit the wrong thing. Okay, thank you. All right, so now I made a data table. Well, I really want this transposed, so I'm going to transpose this. And now I've got a data set that has 100 rows in it, and there's my total hours. Well, I want this to be, really I want this to be dollars now. So I'm going to say this is the total dollars for my 30 units. And I'm going to put a formula in there that just takes my hours times my $50 per hour. And now that's the total dollars. But I said I have a spec limit for that. So I'm going to go up here, and in the column properties, I'm going to put a spec limit in here, and I want this to be no more than $206,236, and I'm going to tell it to add a reference line when I do a graph. And if now I go analyze this, That was dollars. Did I say hours?
Yeah, you got your other term in hours, right?
I just did. That's what I just created a column. Sorry.
I missed it. I'm sorry.
No, that's okay. I created this column that took this hours times the 50. So now I've got dollars here, and I've got a spec limit. So now I can find what's the probability that I am actually going to meet my budget at completion of $600,000. And if I come down here, it does a capability analysis, and it says 99% of the time, I'm going to be above my spec limit. So 99% of the time, I'm not going to meet my budget. So I know now I have a very high risk of not meeting my budget at completion. But I know more than that. I also know by looking at the quantiles, and again, I'm going to do these quantiles in 10%. So now I can look at these quantiles and say, okay, 80% of the time I'm going to be less than $250,000. And so my budget was $206,000. So I'm going to be over by what? $44,000. So 80% of the time I'm going to be over by less than $44,000. So the program now has what's the risk that I'm going to meet this budget, and it's going to know by how much am I going to be over or under. Because this one I'm over, my budget, but other times I might be underrunning. At Raytheon and other companies, I'm sure we all do financial predictions. EACs are vital to Raytheon. The programs have to do this. That's why I got involved in this, is by program managers having to do this, and they really want to understand their risk, not just this one number and base everything on that. So that's how the whole reason I got involved in doing these Monte Carlo simulations. These help us, provide us an estimate of risk. Gives us the risk or opportunities. A lot of times in our case it was risk, but determine the probability. It helps us determine the probability of overrunning and underrunning. It can give us a range of overrun or underrun. Monte Carlo simulations, though, aren't used just in these financial predictions. We can do it in cost estimates, like design to cost, if you've heard of that before. You're designing a product, you're trying to understand how much it's going to cost. I can use Monte Carlo simulations there. I've used them in proposal cycle time. We had a whole bunch of different inputs that happened in our proposals, and we were trying to understand what are the key drivers there. We got ranges from previous proposals. We were able to do Monte Carlo simulations there. We do them in engineering tolerance stack-ups. There's a lot of different uses for Monte Carlo simulations. JMP actually, doing it with the random draws there provides us an easy way to go do that. If people are familiar with the triangular distribution, it's one that's really popular using in Monte Carlo simulations. When you go in there, it's got random triangular distribution. So there's a whole bunch of different distributions built into that. It's just creating those columns to go do that. Now, I know like when you're building models, it's got that already built into there. But I wasn't building a model from regression. I was just adding up numbers. So that was an easier way to go do that. Any questions? Yes.
Hi, Joan. That was an excellent presentation with really good practical implications. So I'm not a statistician, so I'm glad you are. And I wanted to ask you on the AICC and versus the BIC versus the -2 log likelihood. When I look at the help file, it says use the one that you prefer, and that doesn't really help me. So I'm asking a statistician, which one do you prefer?
So I went and tried to understand the AICC, and actually all I found was you found a lot of technical stuff which got way over my head really quickly. I only have a master's in it, so it's not like, but it got over my head quickly. But that's the way that when you do the fit of the distributions, they use the AICC. And so that's why I go take the step further and just make sure that you go look at the goodness of fit test to say, does it really even fit? Because there's times that you'll go fit a distribution, it'll fit one, but it's not a good fit.
So part two of that question is you said that the AICCs were pretty similar. Do you have a rule of thumb that you go by? I've heard 2, I've heard 4.
So when I went looking, I found 2, if it was within 2. But again, I sit there and I've played with the goodness of fit and said, okay, this one's 5 off. Does it fit or not? So that's how I used it. Mm-hmm. Anything else?
Yeah, question on just, it's a jump question. So for the JMP and dot variables, you went in on the actual data, you fit those distributions, and then you had to go in and create another spreadsheet and manually enter in the mean and standard deviations for those distributions in your Monte Carlo simulation. Is there a way in jump which is fine for 4 variables, but if you had 400, that gets a little unwieldy, I think. So is there a way to specify variables in a model and say, go get the distribution from this data and use that in my model? I'm
going to have to open that up to anybody in here from Jump or that knows, because I couldn't find a way.
Okay, but you tried, apparently.
I looked, but I could, there's a lot of things that I don't know, so.
Okay.
Do you know, Brian? Or?
So I'm not going to hijack your presentation. I'm really good at that. But when you use the simulator, you can sample a distribution from another table. So for example, if you were to just make a table that has 2 rows and you have your formula for JMP dot and then times your loaded labor rate and totals, and you just had 2 rows and you put kind of the min and the max in there, then you can run the simulator, go to graph and profiler to profile that formula, and then from that you can start the simulator, and then in that simulator you can go and say that you want a sampled distribution from another table instead of like a fixed distribution, and you can go point at that original table that had their variables in it to get it. And I know that sounds horribly complicated, but if you saw it, you'd be like, oh yeah, that's...
We're going to have to go afterwards and have him show us, so, because I don't understand exactly what he's saying, but I'd like to know, so.
Cool. Thank you.
Thank you. Anything else? I got like 1 minute left before they cut me off. All right, well, thank you.